Energy time uncertainty in the ordered vacuum. The model of the ordered vacuum developed here involves random walks, so uncertainty is introduced into all quantities. The uncertainties in some pairs of quantities are inversely related, as is shown here for energy and time. Consider a free electron executing its random walk. After a small number of steps, the electron seems to have moved a great distance, statistically speaking, relative to the small amount of time, n delta t, it has been moving. This is congruent with an energy much larger than the actual energy of the electron, and hence with a large variance in the energy. However, after observing the electron for larger times, it becomes apparent, again statistically speaking, that the electron has not moved very far. This is congruent with an energy much closer to the actual energy of the electron, and hence a small variance in the energy. Thus, the uncertainty in the energy, delta E sub n, and the duration of the measurement, n delta t, seem to be inversely related to one another. Since the electron is doing a random walk from its original position, then this inverse relationship should be derivable from arguments based on the spread of positions covered by an isotropic random walk. Such a derivation would produce an energy-time uncertainty relation. Let us proceed with the derivation. The distance covered after n steps is S sub n equal to n times the step length, h over 2mc, modified by the statistical factor alpha sub n. Or, of course, alpha sub n has to be between 0 and 1. And this occurs in time delta t sub n equal to n times the step time, h over 2mc squared. This distance expressed in units of the step length, h over 2mc, is r sub n equal to n alpha sub n. Thus, S sub n can be written as r sub n times the step length, h over 2mc. The theory of random walks dictates that the mean and variance of the unitless quantity r sub n are given by the mean equal to the square root of n and the variance equal to n minus 1. After n steps, the observed velocity will be mean of v sub n equal mean of S sub n divided by delta t sub n. The mean of S sub n from 2 bullets up is the mean of r sub n times h over 2mc, and delta t sub n from 3 bullets up is n h over 2mc squared. Doing the cancellations, we're left with c times the mean of r sub n divided by n. And of course, we just found out that the mean of r sub n is equal to the square root of n, so this can be written as c over the square root of n. Since the mean of v sub n is equal to c times the mean of r sub n divided by n, the variance in r sub n will propagate to v sub n as delta v sub n equals c delta r sub n over n, which of course is equal to c times the square root of n minus 1 over n. The electron's energy after n steps is measured to be E sub n equal mc squared divided by the square root of 1 minus v sub n squared over c squared, so that the variance in r sub n propagates through v sub n to E sub n according to delta E sub n equal m times the mean of v sub n times delta v sub n divided by 1 minus the mean of v sub n squared over c squared, all to the 3/2 power, which is obtained, of course, by differentiating the energy with respect to v sub n. Using the expressions for the mean of v sub n and delta v sub n from the last slide, this can be worked down to the form delta E sub n equal mc squared divided by n minus 1. Finally, the product of the uncertainties can be reduced to an expression involving only n and constants. Delta E sub n times delta t sub n equals mc squared divided by n minus 1 from the bullet above this one, and of course delta t sub n is n times h over 2mc squared. Do the cancellations, and this reduces to h over 2 times n over n minus 1. Thus, the product of the uncertainties depends on n, and clearly the minimum uncertainty occurs as n approaches infinity, and is given by delta E sub n times delta T sub n has to be greater than or equal to h over 2. This is our final result. The fact that we get half the usual uncertainty may mean that this uncertainty is always lost in the Heisenberg uncertainty, which derives from the measurement process, not random walk statistics. But the numerical factors on the right-hand side of this inequality depend on what is used for the mean and variance of the unitless quantity R sub n. Interpretations of this result would depend on what is used for those quantities. Thank you for listening.